Greetings, everybody. Learning is a hobby here. I wanted to finally start on my new series where I go through the books of Serge Lang, and I'm going to start with his two sort of high school level books. The first one being this one, Geometry, a High School Course. This has a co-author. This is by Serge Lang and Jean Murrow. So this is a high school level course on geometry, planar geometry. So let's go into my notes and we'll take a look at section 1.1, and I'll post the solutions to the exercises in another video. And then also I plan on posting the videos for section 1.1 and 1.2 for his book on basic mathematics as well today. So uh, look out for those. So anyway, let me bring up my notes here. All right, so like I said, this is section 1.1. All right, so Lang starts out by saying that the geometry presented in this course deals mainly with figures such as points, lines, triangles, circles, etc., which we will study in a logical way. And for the moment, we'll be working with figures which lie in a plane. So you can think of a plane as a flat surface which extends infinitely in all directions. And we'll start with um, an axiom here, which he denotes by LIN, I guess for line. Given two distinct points, P and Q, in the plane, there is one and only one line which goes through these points. And just as a note here, we did denote this line by a capital L with subscript PQ. That notation means the line that passes through the points P and Q, like I have drawn in the picture here. All right, then we get a definition. The line segment, or just segment, between P and Q is set consisting of the points P and Q and all the points on the line LPQ lying between P and Q. All right, and we denote this line segment by this notation here, so PQ with a line segment on top. If we choose a unit measurement, we can measure the length of a segment, which we denote by this notation, d of PQ, that stands for distance between P and Q. And we have a note here. Frequently, we will assume that some unit of length has been fixed and will omit reference to the units. For example, if dpq equals 5 rather than dpq equals 5 centimeters or 5 inches or whatever. All right. Let's see, we have another definition. There's a lot of definitions here because we're just starting. So we define a ray starting from P to consist of the set of points on a line through P, which lie to one side of P and P itself. We also say that a ray is a half line. All right, the ray starting at P and passing through another point Q will be denoted by this notation, capital R with the subscript PQ. All right, and we have another note here. If Q prime is another point on the ray RPQ that is distinct from P, then RPQ equals RPQ prime, so they're the same ray in other words. A ray is determined by its starting point and any other point on it. All right, another definition, the starting point of a ray is called its vertex. And here's some notation. Sometimes we will wish to refer to lines without naming specific points on them. In these cases, we will name the line with a single letter, such as K or L. All right, definition. We define lines K and L to be parallel if either K equals L or K is not equal to L and K does not intersect L. And here's a note. Our definition allows for a line to be parallel to itself. And then we have some axioms here that deal with properties of parallel lines. So this is he denotes these by PAR and then with the number after it. So par 1, two lines which are not parallel meet in exactly one point. Par 2, given a line L and a point P, there is one and only one line passing through P parallel to L. And finally, par 3, let L1, L2, and L3 be three lines. If L1 is parallel to L2 and L2 is parallel to L3, then L1 is parallel to L3. So this is a sort of transitive property. Okay, another definition, two segments or two rays are parallel if the lines on which they lie are parallel. Right, and notation here, if lines L1 and L2 are parallel, then this is the notation we use to denote that. So L with subscript 1, and then two parallel lines, L subscript 2. All right, that means L1 is parallel to L2. Okay, another definition, a fact like Lin, par 1, par 2, par 3, that is accepted as fact without further justification is called an axiom or a postulate. And this concept above that I just mentioned up above is discussed more fully in section 4 on proofs, which we'll get to eventually. All right, another definition, let PQM be 3 points in the plane, not on the same line. Then the triangle determined by PQM is a set consisting of the 3 line segments PQ, QM, and PM. And we denote this triangle by this notation here. So we have triangle PQM. Okay, definition for collinear. We define points to be collinear whenever they lie on the same line. And we have a note here. If PQM are collinear, the segments PQ, QM, PM do not form a triangle. All right. Remark, there's some ambiguity about the notion of a triangle that, the way that we were talking about it, or will talk about them. Sometimes the word is used to denote the region bounded by 3 line segments. One should really say, quote, triangular region. However, we will abuse language and refer to the area of a triangle when we mean the area of a triangular region bounded by a triangle. Although slightly incorrect, it does not really lead to serious misunderstanding. And obviously that's a lot easier to say. So, okay, a couple more definitions. We define a triangle to be isosceles if 2 sides of the triangle have the same length. And we define a triangle to be equilateral if all 3 sides of the triangle have the same length. And just a remark, in mathematics, 2 quantities are said to be equal if they are the same. For example, and then we have a bunch of examples. So here we have 2 line segments, AB and CD, and these 2 line segments are not equal because they are not the same segment. They constitute 2 segments, however, their lengths are equal. So they have the same length or equal lengths, but they are not the same line segment because they don't lie on the same line. Right, according to the definition that we had up above. Similarly, the 2 angles to the left are not equal, but their measures are equal. Right? If we say a point P equals a point Q, then P and Q are the same point, merely denoted by 2 different letters. All right, and I think that's section 1.1. Yeah, the next thing that I wrote down here are the solutions to the exercises, which I'll get to in another video. So section 1.1 was relatively short, and you'll see each of the sections themselves are kind of short. Let me just stop the screen for share for a second. I am kind of excited about, because he has a bunch of straight edge and compass constructions in the book. I'm excited to actually get around to that, but I'm looking for ways to make videos on doing, compass and straight edge construction so that it'll be visible to you guys. So there is a ruler and straight edge and compass construction in the exercise set for section 1.1, but I'm fiddling around with a couple of different ways of filming that. So just bear with me while I figure out the best way to do that. And once I do, I'll post the video for the solutions for this section. All right, I'll see you guys in the next video. I do plan on posting the video for section 1.1 and 1.2 in Lang's Basic Mathematics today as well. So keep an eye out for that, and I'll see you guys in the next one.